Hello everyone, welcome to today's webinar, which is called Cheese 3D Shape and Electrostatic Virtual Screening in a Vector Space. And today I would like to talk about our latest preprint, where we introduce the technical side of cheese and the scientific background of this technology. Feel free to ask any questions in the comments and I will try to live answer them. There will be as well a time in the end to make a discussion. To those who do not yet know our products, cheese stands for Chemical Bending Search Engine and it's a publicly available application on our website where you can freely search by 3D shape or electrostatic similarity in large chemical spaces such as enamine reel, Explore, ChemRxiv, Zinc, or MQ. And I encourage you to give it a try if you don't yet know about it. However, in the paper, we don't talk about cheese search as a product, but as a framework or technology. It's helpful to contrast it to some standard notion where you have a chemical space. The chemical space is consisting of molecules. The molecules have some similarities between them in terms of 3D shape or fingerprint similarities or any other chemical similarities. And to find the active molecules for some targets, you usually do virtual screening by molecular docking, for instance. Whereas in our work, we are just translating this whole process into a vector space, and chemical space for us is just a metric space with measure. Then those molecular similarities are represented as easily computable Euclidean distances between those vectors, and the virtual screening process stands for nearest neighbor search or vector retrieval in our case. I would like to add that we are tackling in this work the task of 3D shape and electrostatic similarity, but in fact, this framework can be adapted to any molecular similarity metric of choice, because there are AI models and they are trainable to any continuous pairwise value between vectors. This is just an illustration to illustrate the section in the paper where we talk about chemical space as essentially a map with a scale, which is, in our opinion, one of the best metaphors and ways how to think about chemical space mathematically and be able to do efficient mathematical operations to navigate in this space. The main contributions or highlights of our work are summarized in this paragraph. There are multiple strong claims. For instance, we are saying that cheese achieves state-of-the-art results in industry standard virtual screening benchmarks, including CLIP PCBA, DUE, and sidechain virtual screening. It competes effectively with leading 2D and 3D methods, as well as molecular docking. The search demonstrates up to 3 orders of magnitude speed up over existing methods, and that's because of square root time complexity instead of linear complexity in traditional methods. Additionally, it achieves a threefold improvement in enrichment factor during multi-ligand evaluation. in a virtual screening benchmark, which highlights its effectiveness is in real-world data sets. And at last, it significantly reduces the cost of the 3D shape or electrostatic virtual screening from more than $50 per query to less than zero on large databases. Here is a summary of the points, so I will not repeat myself, but add two more. Since it's machine learning methods, it's surprising how well cheese generalizes. We have tried it on 12 diverse chemical spaces, which are out of distribution. We will see the benchmark soon. And the molecules it founds are mostly unique and novel. In fact, more than approximately 90% of the molecules found in average are not overlapping with other methods. Speaking of the model architecture, the main component of it is a differentiable encoder with shared weights, which is used to translate an input molecule represented as smiles into a high-dimensional Euclidean space where the vectors are representing ensemble similarities between molecules. The loss function shown in the middle is based on the preservation of the original metric we choose. In our case, it's the 3D shape or electrostatic metric between those molecules/ensembles. So it's the preservation of this metric into Euclidean distances between the vectors in the vector space. For this, similarity preserving embeddings are trained. As a metrics, we are training the models on ESP-Sim and ShapeSim from this paper, which are using conformer alignments and integrals over the volume overlaps or electrostatic fields in 3D. Then it can be illustrated as follows. We are starting with the ensembles computed for the molecules in a pair. And we compute the end-to-end alignment matrix, which means an alignment with all of the molecules in the pair, and choose the maximum, which stands for the best aligned pair of conformers in those ensembles. We end up with this nicely aligned pair of conformers, and then straight proceed with the computation of this ESP-Sim or ShapeSim based on the overlap integrals. Then after this whole training process, I would like to add that it's very computationally heavy. In fact, it can take minutes or even more just for computation of this shape or electrostatic similarity of one pair of molecules. So there is a big space for improvement. And that's why we have chosen these metrics, because they are very computationally heavy. But after the training, a single computation or evaluation of distance between two vectors is super fast, and it can be as well searched very efficiently. The search architecture consists of a vector database And this vector database is basically storage for cheese embeddings. And to optimize this storage for retrieval of nearest neighbors or for search of the most similar molecules, we are clustering all the vectors into similarity clusters based on k-means, then performing a compression to lower the memory of these vectors. So in the end, they are represented by 32-bit PQ codes and no longer the continuous values, which is very efficient in terms of the disk space and RAM needed. Then during the search, we have an input molecule and translate it into cheese embedding. We search the nearest cluster for this vector by searching for the nearest centroid of these PQ of these PQ code clusters, and then we take all the PQ codes and perform an exhaustive asymmetric distance computation to obtain the nearest molecules. To just highlight some of these stats, for instance, in comparison to rocks or fast rocks, that's the table in the bottom, you can see whereas with rocks, it would take 55 CPU years on 64 CPU cores to search in and I'm in real, which is 5.5 billion molecules. With fast rocks, it would take 30 minutes on 200 GPUs. And with cheese, it takes only 6 seconds per query and needs only 4 CPU cores. So there is astronomical difference in the speed as well as in the cost per one search or one virtual screening. Let's now talk about some benchmarks and evaluations we have done. The first kind of a sanity check is retrieval distribution evaluation, which consists of repeatedly searching using cheese, then computing the ground truth 3D shape and electrostatic similarities, and evaluating this across chemical spaces to see how well it generalizes. In this benchmark, we compare cheese just with Morgan fingerprints and random. Here is how this task is set up. For instance, we are searching by this query. This is an example drawn from a search on PubChem database, and you can see the search results from cheese. That's the top 5 best molecules and the top 5 molecules retrieved by Morgan fingerprints. Below are the ESP-SIM values, and here the ESP-SIM values for cheese are higher than for the fingerprints, which mean that the retrieved molecules are more electrostatic similar to the query. It is quite obvious in this case why the scores are higher. It's because the sulfonamides are preserved both in the case of cheese, whereas fingerprints sometimes preserve only one or none, and it's of course electrostatically significant group. So this is what causes the difference. And another example, in case of shape similarity, here we have again a random query, and the top molecules retrieved by cheese and by fingerprints. Here you can see that cheese is more sensitive to the shape of the molecule, even by looking just on the number of the rings. In case of fingerprints, we have molecules that have like 3 rings or even four rings, and you can imagine that it wouldn't be so great in 3D shape alignment. And if you do this 100 times on all 12 of these databases and averages the ground truth ESP-SIM and ShapeSIM values over all the queries, you will obtain distributions like this. Where the more it's move to the right, the higher the retrieval, in contrast to just sampling random molecules from the database. We can see that while cheese was trained only on zinc, it definitely generalizes on all the other databases, and in all of them it's significantly better than random. And it's also visible in some cases, for instance, in the PubChem database, or maybe in these distributions on ChemRxiv, that the orange or red color, which represents cheese shape sim, is moved to the right and better than what is retrieved by fingerprints. In the case of electrostatic similarity, the comparison of those distributions of cheese versus fingerprints are quite overlapping, or the difference is not so clear. In some cases, we can see the cheese distribution is narrower, which usually means that it has a higher median, thus the retrieval is better. But to check whether it even retrieves on average different molecules and learns anything at all, we have looked onto uniqueness of the retrieve results. And for shape similarity, the uniqueness is quite high. Here we can see Venn diagrams in percentages on each of those databases. For instance, in this Campbell Venn diagram, it means that 45 percent was retrieved by cheese, 45 another 45% of molecules were retrieved by fingerprints, and only 10% of those molecules is common. So if we look at it and average all the results, it seems that in all the cases, on average, the molecules retrieved by cheese are highly unique, and in fact more than 80 or 90% of them are different from what's retrieved by fingerprints. Here is it for ESP-SIM. I would like to add that this might not be the case always. For instance, there are some real-world chemical spaces, such as Dell screens. That's one notable example where the distribution of the chemical space might be too skewed or too sparse, so that if you pick like any similarity metric, be it fingerprints or cheese or 3D method or anything else, the retrieve molecules will be the same. So that's some like special edge case which can sometimes happen in the real world, but in these publicly available chemical spaces, it seems that the uniqueness is high. And now let's move on to these ligand-based virtual screening benchmarks we performed. We have stuck with the most established ones, such as LitPCBA, DUDE, and sidechain virtual screenings. And these are benchmarks assembled from protein targets and sets of active and inactive compounds. Usually, the activities are like experimentally measured, and usually the protein targets have as well a crystallographic X-ray structure with ligands to have a proper interpretability of what is the ground truth, and the benchmark methods are scoring mixed set of compounds, and the meta method is a method which retrieves more active compounds from this mixed set. So usually there is an enrichment factor evaluated, which is a percentage of hits retrieved, or rock or bedrock, which is more like classification accuracy of recognizing the actives apart from the decoys. First of these benchmarks is LitPCBA, which is on 149 dose response PubChem bioassays on 15 sets of targets, and there are targets with at least one X-ray structure and more than 400,000 active and inactive compounds. This benchmark has as well an unbiased version using a procedure called asymmetric validation embedding. That's very important because these ligand-based virtual screening benchmarks are notoriously tricky in the way that it may favor machine learning methods by an artificial bias in those to the structures of the molecules. So in contrast to the UDE, this benchmark uses an advanced debiasing methods to make an objective validation procedure. In a single ligand evaluation, which means that we have one ligand, we are searching by the ligand and scoring the active and inactive compounds in a validation set based on similarity to this ligand. Cheese performs the best, both from ShapeSim and ESPSim. You can see that after cheese ESPSim, there are ECFP4 fingerprints, then Surflex, Doc, and well-known ROX combo 3D similarity. We can also see in bold the targets where the mean enrichment factor for 1% is higher than 5. So there are some cases, for instance, the very first target where only cheese finds something interesting or finds some active compounds, and then there are also other cases. If we can discuss it in the discussion, if there are any follow-up questions. And then there is a multi-ligand evaluation, which means that we are not searching only by one ligand, but in fact we are searching by a set of active compounds. And this is commonly used in real-world screenings, where you have multiple active compounds and you can search them one by one, and then take the average similarity of unknown compound to these actives to evaluate the probability of whether it's active as well. Or in this case, there is a max pooling or batch search procedure, which means that we are taking the maximum similarity of the unknown compound to any of the actives. To summarize, it's basically a set search technique where we have a set of ligands and we want to retrieve any more. We want to enrich this set of actives by the molecules in the database. Here it is interesting that only cheese performs like very well in this multi-ligand evaluation, whereas other methods, be it fingerprints or SurFlexDoc or rocks, mostly fail. This evaluation, to be consistent with the previous literature, corresponds to maximum similarity method, as the formula is here in the table. But we have also tried many more set similarity metrics inspired by literature in optimal transport and 3D point cloud registration, or in general in machine learning. And these are different ways how to perform the set similarity. For instance, we can include as well a set of inactive compounds and then measure maximum similarity to actives and minimum similarity to inactives. Or we can take mean similarity instead of the maximum similarity, or compute centroids of these sets and then assess distances of these centroids. In this case of evaluating other formulas, we discovered that in case of batch 3D shape similarity search, in fact, the active-inactive formula works the best. And in some cases, it's understandable that it might help a lot to include as well this set of inactive compounds and then optimize for the joint similarity and dissimilarity. And in case of ESP-SIM, the best performing was optimal transport, which is the most mathematically advanced method how to do set similarity properly using techniques from measure theory and related mathematical fields. However, in practice, in cheese we are using this batch KNN, which is basically the same as maximum similarity, but it's more memory efficient because it doesn't compute the whole similarity matrix, but only similarities to the nearest molecules or to those retrieved by the search. You can post the questions if you have any thing to ask. I will like skip the details, but it might be super interesting field in future to see in visual screening what of these metrics is the most performing one, and there's a lot more research to be done. The advantage of cheese is that since there are these vector embeddings, it's much easier to implement all the existing methods to do this, whereas with binary fingerprints and Tanimoto's similarity, it wouldn't be even possible. Now we have the directory of useful decoys enhanced benchmark. On the right, you can see distribution of target classes represented in this benchmark, which consists of 102 targets and more than 20,000 clustered ligands drawn from Campbell. And each of them has property matched decoys drawn from zinc. Here we have evaluated again rocks, both color and shape. Then USR, which computes shape similarity by statistical moments in L1 embeddings. And we have benchmarked as well AutoDoc-Vina, a well-known docking method, and WAMS, which is 3D shape similarity based on voxel grids. And here are the results across these target classes. In most of them, you can see that, again, cheese ESP sim as well as shape sim works very well. To clarify what is on the y-axis, here we are using Bedrock, which is basically a weighted receiver operating characteristic, and with alpha 20, which is the coefficient used here, it means that roughly 2% of the molecules of the top scoring molecules make for 80% of the result. There is a problem with just taking a rock score, so that's why there is usually this weighted bedrock used, because it's more reliable or more closely represent what we want to measure in this virtual screening scenario, where the top retrieved molecules are the most important ones. To wrap it up, you can see that on all the mixed or miscellaneous targets, the results are very, very solid. On protein kinases, the shape, cheese shape sim performs better than ESP sim. On nuclear receptors, it's comparable or slightly worse than ROX. And on other target classes, there are not many samples, so it's hard to judge. Here is it again averaged over all these targets. And there is now another evaluation where we have taken benchmarks of docking methods such as Gold, Glide, Glide from Schrödinger, Flexis from Biosolvate, or Sarflex Doc. And some of these docking methods, notably Gold and Glide, are better than cheese, but it outperforms Flex and Surflex. You can notice also that the variance is very high, so it's probably says about something about the noisiness present in the benchmark. And the last of these three benchmarks is sidechain virtual screening, which is a benchmark assembled from 400 Campbell assays and on 202 targets, where there are mined matched molecular pairs of actives and inactives. What does it mean? You can see in the figure that there are molecules which have the same context, so large portion of the molecule stays the same, be it the active, inactive, or the ligand, and then only the side chain is different. So the method to perform well, it needs to be able to recognize bioisosteric side chains to the ligand and avoid those inactive R groups. Now, in this benchmark, there was evaluated Spark, Glide, Smina, which is another docking method, and RDKit fingerprints. And these are the results. I have said that evaluation in terms of ROC is not optimal in virtual screening benchmarks, but this is more akin to this benchmark is more akin to some classification task where you need to distinguish the active side chains from inactive ones. So in my opinion, it's appropriate to use it. And here cheese was outperformed by Spark, but the difference is not so huge, especially if we take in account the variance, and it performed even better than Glide, RDKit fingerprints, Smina, or the other methods. Also, the rocks are quite high in this case, so we can say it works reliably for distinguishing the correct bioisosteric compounds. Okay, that's all for this presentation. Yeah, I hope I have summarized some of the main points or benchmarks performed in the paper. And feel free to ask any questions. There is a lot of details I have omitted, which are present in the paper or in the supplementary material. So you can ask. You can ask now. Yeah, I will just find the section with the questions. Okay, one question is if it was Glide SP or Glide XP. The version is specified in the paper. It was Glide SP from Schrödinger release 2017 2. So that's I hope the answer. That was the sidechain virtual screening, and in the DE it was version 6.3 from Schrödinger. By the way, thank you for your time. I'm excited by the feedback and reactions I got on the paper, and you can as well read it in your free time and send me an email or contact me here or LinkedIn and I will be eager to answer for anything or explain the supplementary materials in Zenodo. So, okay, if there are no more questions, this is all for today's webinar, and I'm looking forward to seeing you again next time.